Okay, folks, it's the next video for finishing up our heating and cooling of naphthalene lab. Here you have your beautiful, gorgeous, well manicured graph posted into your assignment. Now, the one thing that makes this a real advanced, top-notch piece of work here would be to write a little analysis statement below your graph. And so wherever your graph ends, if you go right below it, I like to use the asterisk, which is right above your number 8, and to type a little blurb, a little statement in here about exactly what is happening. Okay, so I'm probably going to describe this graph like so. This graph shows, and what are we showing? The heating of naphthalene. There is a distinct plateau. Oops, that's not spelled right. Plateau. Don't mind my terrible spelling habit there. Let's see, why is this spelled wrong? Naphthalene. I think I've been spelling that wrong the whole time. So this graph shows the heating of naphthalene. There's a distinct plateau at 80 degrees Celsius from about 5 to 7 minutes. After that, the heat keeps increasing. At the, I don't know, what are we, 11-minute mark? The temperature begins to cool. Again, there is a plateau at the 80 degrees Celsius mark around, I don't know what time we got there, about from 16 to about 19 minutes. Okay, so that pretty much describes what we're seeing. We're seeing the heating of naphthalene. There's a distinct plateau at 80 degrees at 5 to 7 minutes. After that, the heat keeps increasing at around 11-minute mark. Temperature begins to cool, and again, there's a plateau at the 80 centimeter mark around 16 to 19 minutes. And that is pretty much a nice summarized statement of what the graph is depicting or showing. Okay, so this lovely little statement here makes a nice little blurb about, what is being shown in the graph. And this way, if someone who had no idea what you were talking about was looking at your graph, they then could read this and get a little bit more of an analysis about what they are looking at. Okay. Remember that when you're completing any sort of lab report, lab summary, you want to write for the people who have no idea what you're talking about. Pretend like I'm, as in your teacher, I'm not the one who's going to be assessing this. Somebody else is going to be reading it for understanding of their own. And so you're writing to inform the general public who might have no idea what you're talking about. So anyway, moving on. Following this graph, we had several questions that we needed to answer. And so in looking at this particular graph, the very first question that you needed to answer was, how can you determine the melting and freezing point of the substance, and what are the melting and freezing point of the substance, and how did those values compare? So that was our initial first question. And if you're looking at the way you broke down your little summary here at the bottom of your page, or at the bottom of your graph, you realize that there are two very distinct places, both during the heating and the cooling of this substance, naphthalene, and it happens at the 80 degrees Celsius mark. So based on this, both the melting and freezing point are 80 degrees Celsius, which can be found on the plateaus of the graph. And then considering the diagonal region of the heating curve as As the sample is being heating, what does the temperature change indicate about kinetic energy of the particles? Now, hopefully you went through and watched the video notes that I posted about the kinetic molecular model of matter and how phases change from one to another. And that should have helped you answer these. Okay, so that temperature change indicates an increase in kinetic energy, so the particles begin to move faster during that diagonal region. So during this region right here, from the 0 to the 5-minute mark, this is that diagonal region. You can picture a trend line kind of just following straight what is kind of happening right there, right? And then you have that plateau. So describing the shape of your graph during the actual changes of state. Is it flat? Is it diagonal? Were they zigzag? What was the actual shape while the substance was in that first part melting? So your shape of the graph during the phase change is flat. It's that plateau, okay? It basically showed you the time it was taking your actual substance to complete its phase change, which is why at that temperature, we see that plateau. That's the place where it stays right there. So it's the time it took that substance in this particular case to melt, right? An increase in heat would melt the substance from a solid to a liquid. So during the heating process, heat is continually being supplied to the sample throughout the experiment. Why does it remain constant? Explained in terms of what's happening to the molecules. Well, during that plateau, where our temperature is remaining constant, those molecules are starting to really move a lot more and spread out. That's what causes it to move from its solid to liquid phase. Okay, so I just said the same thing. It remains constant because that's the time it takes those molecules to complete its change in phase. Now, the opposite of this, the diagonal region of the cooling curve, right? So on that other half from the 11-minute mark on, when it's cooling, what does the temperature change indicate about the change in kinetic energy? Well, if it's cooling down, right, those molecules are going to start to really move slower, which means they are losing energy. They're going to start coming a little bit closer together as energy is being released, right? Heat is kinetic energy, and so as heat energy is cooling, we're losing some of that motion in the molecules. Okay, so in number 6, during that cooling process, heat is continually being removed from the sample, yet it remains constant during the freezing, right? So this is a phase change at that particular section where you have that liquid now moving back into its solid state. If that temperature indicates no change in kinetic energy, what is changing? Well, kinetic energy is energy of motion. And so if there's less motion, there's a transfer or transformation of energy into what we call potential energy, which is stored energy. So it's going to store the energy in between the bonds of molecules and their intermolecular forces. We're going to really store that energy right in there and convert it back to its solid form. And remember that, you know, molecules, even in their solid state, do move. There's a small amount of energy that's going to stay in there, but it is not moving as fast as it was in its full liquid state. Hopefully you were able to follow along with this video and to help yourselves answer these particular questions. If you should need me in any way, shape, or form, please feel free to email. And have yourselves a lovely day. Please make sure you're reading the agenda. And good day.